Good morning all. This is Dr. Abdul Pasha. We are in the course of Power System Operation and Control. So today's topic is about numerical analysis on incremental costs. So earlier we have gone through the incremental costs. These are obtained from input-output characteristics, and these will define you the plant how to meet the demand requirements, cost analysis, comparisons during hydrothermal scheduling processes, and coming to the load demand case, based on the demand, how the generators will generates the power and how to meet the load requirement. We will see here some numerical analysis, and this will gives you the how the plant will meet the load requirement. So coming to the incremental production cost, that should be given for a particular unit is supposed to be made up of the incremental fuel cost plus incremental cost of the given items, like the working labor, suppliers, maintenance, and availability of the water. So these are some of the constraints to consider for the incremental production cost for a given unit. So it is necessary for a rigorous analysis to be able to express the costs of the production items as a function of the output case. So however, no methods are presently available for expressing the cost of the labor, supplies, or maintenance accurately as a function of output. So we need to treat it as a separate case, individual of the whatever it may be the constraints we consider, that is labor, suppliers, or regular maintenance of the power plant. Whatever it may be hydel, or it may be thermal case. So we need to treat it as separate parameter. Here we will go with one simple example for considering two power plants. So here the problem is given like this. Consider two units of a plant. Here we have a simple one plant containing two units. This is unit 1 and this is unit 2. So only one plant. The number of units we are considering 2 units. The units may be more, 4 or 5, whatever it may be. We are here making the analysis for 2 units. So consider 2 units of a plant that have fuel costs. So here fuel costs are given in terms of F1, F2. So where F1 is equals to 0.8 by 2 P1 square plus 10 P1 plus 20. This is the fuel cost of first unit, F1. Next, fuel cost of second unit, that is F2. So that is 0.7 by 2 P2 square plus 6P2 plus 20. So here the fuel costs are expressed in rupees per hour, that we already discussed earlier. Once again, for F1 and F2 fuels, the fuel costs are in rupees per hours. Then the incremental cost will be, the incremental cost is given in terms of lambda 1. So lambda 1 equals to df1 by dp1. What df1 by dp1 enables means, the df1 by dp1 enables incremental cost. df1 by dp1 enables incremental cost, which is about 0.8 p1 plus 10. 0.8 p1 plus 10. So every value is considered here, the product of first unit power and second unit power. If it is the case of first unit parameters, then the product of first unit parameter is considered with the power generated with the first unit. That the units are considered in rupees per megawatt hours. Here, the first unit power generated is considered as an incremental cost in rupees per megawatt hour. So here df1 by dp1 is the change, that is incremental fuel cost. So here we are considering lambda 1 means that is the first one, first unit. For that first unit, the incremental fuel cost is df1 by dp1, where df1 is the incremental fuel cost with respect to the power, its power, that is dp1. So fuel cost is in rupees and the power coefficient is in megawatt hours. Like that we will consider. And lambda 2 is equals to df2 by dp2. This is the incremental fuel cost of second unit. dft by dp2. df2 by dp2. So where df2 is the fuel cost, change in fuel cost of second unit, where dp2 is the change in power output for second unit dp2. So that is about 0.7 p2 plus 6. So here also these units are same in rupees per megawatt hour. So if these two units together supply a total of 220 megawatts, means here total power is given, that is 220 megawatts. Individually it is divided as P1 and P2. So that is P1 is 100 megawatts, P2 is 120 megawatts. So the first power is about only 100 megawatts, but coming to second P2, that is about 20 more, that is 120 megawatts. So will results in an incremental cost of lambda 1 equals to 80 plus 10, that is 90 rupees per megawatt. And lambda 2 is about 84 plus 6, that is 90 rupees per megawatt. So this implies that incremental costs of both the units will be same. If you observe, the lambda 1 we got is 90 rupees per megawatt hour. Lambda 2 is 90 rupees per megawatt. So both the incremental costs are same. That is, cost of 1 extra megawatt of generation will be about 90 rupees per megawatt. Even though if you consider 1 extra megawatt hour of generation, that will result to 90 rupees per megawatt. Then we have F1. That means if you go with the previous expression, 0.8 by 2 P1 square plus 10 P1 plus 25. In that expression, if you substitute that P1 value, P1 is given here as 100 megawatts. Then if you substitute in the first one, that is F1, that is about 0.8 by 2, 100 square plus in the expression 10 P1, 10 into 100. Here plus 25. So plus 25, which is equals to 5025 rupees per hour. So this is the incremental fuel cost of unit 1, that is F1. Similarly, the same analysis if you considered here for the expression F2, 0.7 by 2 P2 square plus 6 P2 plus 20, then F2 equals to 0.7 by 2. In place of P2, you substitute here 120, then here it will becomes P2 square means 120 square plus 6 into P2. P2 means again 120. So 6 into 120 plus 20. That gives a value of 5780 rupees per hour. And total cost of the generation is P. So here total fuel cost is F suffix T, that we can write it as F1 plus F2. If you add these two combinations, this one and this one, will results to 5025 plus 5780. That will gives you 10,805 rupees per hour. This is the total fuel cost. Now we should assume that if you operate instead with the P1 is 90, P2 is 130. What is the total sum of these two? P1 plus P2, 90 plus 130 means that is about 1 to 20. Here P1 plus P2 is 220. Earlier also what we have? Earlier 100 and 120 combination. That summation gives you 220. Here with these values, if P1 is 90, P2 is 130, their summation also 220 megawatts. Then individual costs of each unit. Each unit will be F1 is equals to, in the equation, 0.8 by 2 P1 square plus 10 P1 plus 25. In that expression, you need to substitute P1 value here. What we assumed here, P1 is about 90 megawatts. So substitute that 90 megawatts here in P1 square plus. Then it becomes 0.8 by 2 P1 square means 90 square plus 10 into 90 plus 20. So this gives you a value of 44,165 rupees per hour. 4,165 rupees. Similarly, if you substitute F2 here in place of P2 square, then F2 equals to 0.7 by 2 P2 square plus 6 into P2 plus 20. That gives you a value of 6,170. Now add these two, 4,165, 6,175. This will be 10, 7, 7, 14, 3, 10. So this is about 10,880. So total fuel cost when you considered P1 as 90, P2 as 130 is 10,880 rupees per hour. So this is the value you get. So whatever we solved for 100, 120 combination, the total cost is about 10,805. If you change it with 90 and 130, you will obtain total fuel cost about 10,880 rupees per hour. So what is the difference you seen here means, here it is about 10,805. Here 10,880 means there will be a hike in the second case of total fuel cost. So this implies that additional cost of 75 rupees is happened for each hour of operation with this non-optimal setting. So how much we obtained as incremental or additional? 75 rupees. So it can be shown that if the load is shared equally by the two units, that means P1, P2 are same, sharing the same load with a value of 110 megawatts. Then what happens means the total cost is again 10,880. Whatever it may be, if the load is, first load is some less compared to second load, and also the case of equally sharing the load, you may obtain the same total fuel cost. If you consider there at 100 and 120 range, here you considered here 90, 130, with equal sharing of the load P1, P2 as 110, then you may got the same total cost, that is about 10,880 rupees per hour. Now, if you move for the second example, here let us consider a generating station that contains a total number of 3 generating units. There in the previous section we considered only 2 units. Here total number of units are 3. So fuel costs of these units are given by F1, F2, F3. So what about F1 here? F1 is about 0.8 by 2 P1 square plus 10 P1 plus 25 rupees per hour. Next F2 is 0.7 by 2 P2 square plus 5 P2 plus 20 rupees per hour. F3 is 0.95 by 2 P3 square plus 15 P3 plus 35 rupees per hour. So the generation limit of the units are 30 megawatt less than or equals to P1 less than or equals to 500 megawatts. And the second one is 30 megawatts less than or equals to P2 less than or equals to 500 megawatts. And the third case is 30 megawatts less than or equals to P3 less than or equals to 250 megawatts. So total load that these units supply varies in between 90 and 1250 megawatts. This is the variation. Now assuming that all the 3 units are operational all the time. Here it should be mentioned that 3 units are running at a time. 3 units are running. We have to calculate the economic operating settings as the load, the incremental costs of these units when it is given with df1 by dp1, df2 by dp2, df3 by dp3. df1 by dp1 is 0.8 p1 plus 10. df2 by dp2 is 0.7 p2 plus 4. df3 by dp3 is 0.95 p3 plus. So all these are mentioned in rupees per megawatt hours, where df1 is the change in fuel cost, that is incremental fuel cost 1, and df2 also 2, df3 also 3. And the respective denominators are dp1, dp2, dp3 are the change in powers for 3 unit cases, that is dp1, dp2, dp3 respectively. So their values are mentioned: 0.8 p1 plus 10, 0.7 p2 plus 5, 0.95 p3 plus 50. All are in rupees per megawatt. So at the minimum load, the incremental cost of the units are minimum load case. What are the incremental fuel costs that we need to consider here? So we are given with the P1, P2, P3 values. So that is about here. That means 90 megawatts are going to be divided. That means each one is 30 megawatts, 30 megawatts. So you need to substitute the P1 30, P2 30, P3 30 value. So P1 is 30, P2 is 30, P3 is 30. Now substitute here. df1 by dp1 equals to 0.8 by 2. P1 square means 30 square, here plus 10. So plus 10. When you simplify this, 0.8 by 2. So that means here it will be 10, means 24 plus 10. That means 34 megawatt rupees per megawatt hour. Similarly, here 0.7 by 2 30 square plus 5, which gives 26. And here 0.95 by 2 30 square plus 15, which gives 43.5. So these are the values we obtained for respective unit: 34, 26, 43.5. So all are in rupees per megawatt hours. So since the units 1 and 3 have higher incremental costs, what is the incremental cost of first unit? 34. What is the incremental cost of third unit? 43.5. Means the first unit and first unit and third unit have higher incremental fuel costs. They must therefore operate at 30 megawatts each. So here the point is that we got first and third one as higher incremental fuel cost. Then here it should must run or operate at 30 megawatts each, whatever the first and third unit. So incremental cost during this time will be due to unit 2 and will be equals to 26 rupees per megawatt hour. So with the generation of unit 1 and 3 will be the remaining constant. So generation of unit 2 is increased till its incremental cost is equal to that of first and third. That means the unit 2 cost is about 26 rupees per megawatt. So it should reach to 34 rupees per megawatt. Okay. So this is achieved when P2 is equals to a value about 41.42 megawatts. If P2 is supposed to be 41, then only you can reach this one. So that is at a total power of 101.4286 megawatt. An increase in the total load beyond the value of 101.42 megawatts is shared between the 1 and 2 units. So their incremental costs are equals to that of unit 3, that is about 43.5 rupees per megawatt. So this point is reached when P1 is 41.87 megawatts and P2 is 55 megawatts. Now the total load that can be supplied at that point is equals to 126 rupees. So from this point onwards, the total load is shared between 3 units in such a way that the incremental costs of all the units are similar. Likewise, we can set the same price. Now it is the case of economical division of a plant load between generating units in a plant. The thing is that we should make the economical division. Why? Because to meet the load demand or load requirement, the behind concept is economic division. When you make the economic division, then only the plant cost will operate suitably. So that plant load between the generating units in a plant. So various generating units in a plant generally have different input-output characteristics. These are not fixed. Why? Because the feeding input may differ to the generator and the generating output also different. So based on that feeding and getting the output aspect, the input-output characteristics may differ. Suppose that the total load in a plant is supplied by 2 units and that the division of load between these units is such that incremental cost of one unit is greater than that of other unit. So these are the changes we may expect. Now suppose Some of the load is transferred from the unit with higher incremental cost to the unit with the lower incremental cost. Reducing the load on the unit with higher incremental cost will result in greater reduction of the cost. That should be taken place than the increasing cost of adding the same amount of the load to the unit with lower incremental cost. So this is happened due to the changes in their characteristics of input and output cases. So these will reflect the incremental cost indirectly. The input output characteristics will indirectly changes these as incremental cost. The input output characteristics will change these incremental costs. So the transfer of load from one to other can be continued with a reduction of total cost. Total cost will be reduced until the incremental costs of the two units are equal. Until the incremental cost of two units are. So if you observe the characteristics here, this is the incremental cost on one axis and this is the power on another axis. So here we are assuming two units. The number of units are two. Number of units are. So when you consider for the first unit, that should be like this. This is the first unit and this should be like this too. So the incremental cost for the first unit as like this. IC1 is the incremental cost 1 for the first unit. And IC2 is the incremental cost of the second unit. So what is happening here with respect to the power generations P1 and P2, the incremental costs also increasing for the respective unit. So initially if you assume IC2 is greater than IC1, what it means? The incremental cost of second unit is higher than the first unit. That is IC2 greater than IC1. There will be decreases the output power in unit 2. So here decremental of output power will happens in the second unit. That is by delta P and increase output power in unit 1 by delta P. Means on the one side there will be decremental by delta P, on another side incremental by delta P. These two will simultaneously happens. Now IC2 delta P greater than IC1 with the delta P, thus there will be more decreasing cost. There will be more decreasing cost and less increasing cost, bringing the total cost less. So this change can be continued until IC1 is equals to IC2. So at which total cost will be minimum. By this, the total cost will be minimum with this consideration. So the same reasoning can be extended to a plant with more than two generating units also. So in this case, if any two units have different incremental costs, any two units have different incremental costs, then decreases the output power in unit having higher incremental cost and increases the output power in unit having lower incremental cost. When this process is continued, a stage will reach wherein incremental costs of all the units will be equal. So, number of units will be getting the equal values. Now, the total cost of generation will be minimum. Thus, economical division of load between the units within a plant is that all the units must operate at the same incremental cost. So, likewise, we can maintain the same incremental cost. Now, we consider another analysis considering a plant having n number of generating units. Then input-output curve of the units are denoted as C1 of P1, C2 of P2. This will take place up to Cn of Pn. These are called input-output curve of the units. Up to the n number of units, Cn of Pn. Our problem is here for a given load demand PD. PD is the load demand. Now we need to calculate the set of Pi. which minimizes the cost function CT, that is C1 of P1 plus C2 of P2 up to so on Cn of P. So which will be subjected to the constraints, the whatever the load demand minus total load P1 plus P2 up to so on n number, which is equals to 0. And Pi is minimum less than or equals to Pi less than or equals to Pi max. Then I equals to 1 comma 2 comma up to so on n. So omitting the inequality constraints for the time being, the problem to be solved becomes minimize the total cost, that is CT, which is about to summation I equals to 1 to n Ci of Pi, subjected to PD minus summation I equals to 1 to n Pi equals to 0. So these may subjected to change. We need to minimize this consideration, and we also make this load demand, which will be subtracted from this Pi, as it may changes from I equals to 1 to up to so on. And this optimizing problem with the equality constraint can be solved by the method of Lagrangian multipliers. So in this method, the Lagrangian function is formed by augmenting the equality constraints. So that is happens to the objective function using proper Lagrangian multipliers. So for this case, Lagrangian function can be written as L of P1, P2 up to so on Pn lambda, which is equals to summation I equals to 1 to n Ci Pi plus lambda Pd minus summation I equals to 1 to n Pi, where lambda is the Lagrangian multiplier. Now this Lagrangian function has to be minimized with no constraints on it. The necessary condition for minimum are dou L by dou P1, which is equals to 0, I equals to 1 comma 2 comma so on n, and dou L by dou lambda equals to 0. So for a plant with the 3 number of units, L of P1, P2, P3, P lambda is C1 P1 plus C2 P2 plus C3 P3 plus lambda Pd minus P1 minus P2 minus P3. The necessary conditions for the minimal are dou L by dou P1, which is equals to dou C1 by dou P1 plus lambda of minus 1, which is equals to 0, dou L by dou P2, which is equals to dou Ct by dou P2 plus lambda of minus 1 equals to 0. Similarly, dou L by dou P3, dou C3 by dou P3 plus lambda of minus 1, which is equals to 0. So finally here, the dou L by dou lambda is equals to Pd minus P1 minus P2 minus P3, which is equals to 0. So generalizing the above necessary conditions, dou Cy by dou P minus lambda equals to 0, which is I equals to 1 to up to so on n, and Pd minus lambda equals to 1 to n, Pi equals to 0. So here dou Ci by dou Pi is the change in production cost in unit, I for small change in generation unit. So change in generation unit will affect the production cost of this unit as alone. Then we can write dou Ci by dou Pi equals to dCi by dPi. So using the equations of 11 with the equation 9, then dCi by dPi equals to lambda, where I equals to 1 comma 2 comma so on. So thus the solution for the problem will be minimized with Ct as summation I equals to 1 to n Ci Pi subjected to Pd minus summation I equals to 1 to n Pi 0, which is obtained when the following equations are satisfied, that is dCi by dPi equals to lambda, where I equals to 1 comma 2 comma so on n, and Pd minus summation I equals to 1 also Pi value 0. So that two conditions gives n plus 1 number of equations which are to be solved for the n plus 1 number of variables, where lambda P1, P2 up to so on Pn equation, this will simply says that at the minimum cost of operating point, the incremental cost for all the generating units must be equal. So this condition is commonly known as equal incremental cost. So this is known as power balance equation. We already seen earlier power balance equation. So another example with C1, C2 values are considered. This represents cost characteristics of two units in a plant. which is 0.4 P1 square plus 160 P1 plus K1, 0.45 P2 square plus 120 P2 plus K2. All are in rupees per hour. Where P1, P2 are power outputs in megawatts, we need to calculate optimum load allocation between two units when the total load is 162.5 megawatts. What will be the daily loss of the units? So incremental costs are IC1, IC2, that is 0.8 P1 plus 160 rupees per megawatt. This is 0.9 P2 plus 120 rupees. Now with these two expressions, when you add total loads, you may obtain 162.5. Here this value is added to here, and here you may obtain lambda value. So lambda is 210 rupees per megawatt hour. Knowing the values of these by optimum load allocation, P1 is about 62 megawatts, P2 is 100 megawatts. When you equate these two, 81.25 megawatts, we have deviated from the optimal value, that is P1, P2. This is 62, this is 100 megawatts. So knowing the values of C1 and C2, the daily loss can also be calculated by calculating the total cost CT, which is C1 plus C2 for the two scheduled values. Now daily loss is 24, that is 24 hours into this CT of product value, which is about 17,171.87. So with this analysis, we can make the better scheduling of the thermal and tidal power plants. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.